Two new airplanes crashed about 4 months apart, minutes after takeoff. In both cockpits, crews fought a system they had not been clearly told existed. A single bad sensor could summon it. Software could push the nose down again and again. The airplane in front of them did not match the airplane they had been trained to expect. The public story became MCAS. The deeper story is why MCAS had to stay almost invisible. The MAX had to look, train, and sell, like the old 737 while flying around a new physical reality. When that contradiction reached line service, 346 people died. To understand why the contradiction existed, start with the 737 itself. The Boeing 737 first flew in 1967. Over the following 5 decades, it became the world's best-selling jetliner, accumulated an enormous global maintenance and training infrastructure, and underwent continuous revision and modernization, while retaining enough commonality across variants that pilots could transition between versions with limited additional training. That commonality was not incidental. It was commercially valuable. Airlines operating mixed fleets of 737 variants could schedule pilots across aircraft types, reduce training costs, and avoid the expense of full-type rating transitions. The 737's longevity was inseparable from its reputation for consistency. In December 2010, Boeing's primary competitor launched the A320neo program, featuring more fuel-efficient engines. The announcement was a significant competitive event. Airlines responded with interest. Boeing faced a choice: develop an entirely new aircraft, which would take years and cost billions, or modernize the 737 again. Boeing chose to modernize. The result was the 737 MAX. The MAX used a new engine, the CFM LEAP, that was larger and more fuel-efficient than its predecessor. The engine's size required it to be mounted differently on the wing, further forward and higher up than on earlier 737 variants. That repositioning changed the aircraft's aerodynamic behavior at high angles of attack. Specifically, under certain conditions, the new engine placement caused the nose to pitch up more than it had on previous variants. This was a handling difference that could, in principle, require pilots to learn new procedures, or require a new type rating. Either outcome would erode the commonality argument. The training cost advantage, one of the central commercial justifications for the MAX program, depended on the MAX flying like a 737. So Boeing designed a software system to make it fly like one. The maneuvering characteristics. Augmentation system, MCAS, was introduced to compensate for the MAX's changed pitch behavior at high angles of attack. When the system detected conditions that could lead to a nose-high attitude, it automatically pushed the nose down by trimming the horizontal stabilizer. In its original design, MCAS was a relatively limited system. It operated in a narrow flight envelope, moved the stabilizer a modest amount, and was not considered significant enough to require prominent disclosure in the Flight Crew Operations Manual. The FAA's certification process, which delegated substantial technical review authority to Boeing's own engineers, did not flag it as a major new system requiring special pilot awareness. Then the design changed. As flight testing proceeded, the parameters of MCAS were expanded. The system was authorized to move the stabilizer more, up to 2.5 degrees per activation, compared to the original 0.6 degrees. It was authorized to activate repeatedly if the triggering conditions persisted, and it continued to rely on input from a single angle of attack sensor. A single sensor. On an aircraft where the system that read that sensor could push the nose toward the ground with enough authority to overpower a crew that did not know what was happening, or was not clearly prepared for the precise sequence of actions needed to stop it. When the 737 MAX entered service, pilots were not told MCAS existed by name. The system was not described in the standard Flight Crew Operations Manual. The training materials that accompanied the MAX's entry into service were designed around the commonality argument. The MAX was presented as a familiar aircraft with improved engines, not as an aircraft with a new automated flight control system that behaved in ways previous 737s had not. The rationale was coherent within its own logic. MCAS was designed to make the MAX handle like a 737. If it worked as intended, pilots would never know it was there. Describing a transparent background system in detail would raise questions about why it was needed, which would raise questions about how different the MAX actually was, which would undermine the commonality argument that justified the limited training program. The system was hidden from pilots not through malice, but because its visibility would have cost too much. On October 29, 2018, the crew of Lion Air 610 encountered repeated uncommanded nose-down inputs, beginning shortly after takeoff. The aircraft's angle of attack sensor, the left one, which fed MCAS, had been providing erroneous readings since a previous flight. The crew fought the inputs. The aircraft pitched down. It entered the Java Sea at high speed. The flight data recorder from Lion Air 610 showed clearly what had happened. Boeing and the FAA were informed. An emergency airworthiness directive was issued. It described a runaway stabilizer condition and directed pilots to follow existing procedures for handling it. It did not name MCAS. Ethiopian Airlines. Flight 302 departed Addis Ababa on March 10, 2019, 4 months after Lion Air 610. The crew encountered the same system, the same failure mode, the same inputs. They had been issued the directive. They attempted the runaway stabilizer response described after Lion Air. It was not sufficient to save the aircraft. 157 people died. The 737 MAX was grounded worldwide 2 days later. To understand how this happened, you have to trace 5 conditions that were present long before either aircraft took off. The first, a competitive business pressure became a design requirement. The decision to match the A320neo's timeline by extending the 737, rather than developing a new aircraft, placed a specific constraint on the MAX program. The result had to be certifiable as a variant of an existing type, with training differences that airlines could manage within their existing 737 programs. That constraint was not an engineering requirement. It was a commercial one. But it shaped every subsequent engineering decision, because any outcome that threatened the commonality argument threatened the program's competitive rationale. The second, MCAS grew in authority during development. The system that entered service was not the system originally designed. The expansion of MCAS's authority, more stabilizer movement, repeated activations, the same single sensor input, was driven by flight test results that required more compensation than the original design had provided. Each expansion was reviewed and accepted within the program. None triggered a reassessment of whether the system had become something qualitatively different from what had originally been certified. A system that started as a background trim function had become, by the time it reached service, a powerful automated input capable of forcing the aircraft into a dive. The process that evaluated it was calibrated to the system's origin, not its final state. The third, single sensor dependency was accepted as sufficient. MCAS relied on one angle of attack sensor, a single point of failure in a system with the authority to override pilot inputs. The rationale, as documented in the subsequent investigations, was that MCAS was intended as a supplement to existing protections, that other systems and procedures would catch a sensor failure before MCAS became dangerous. That assumption required pilots to recognize a failure mode that had not been described to them in an aircraft they had been told was like the one they already knew, under high workload conditions, in the seconds after takeoff. The fourth, pilot knowledge and training were limited to preserve aircraft commonality. The decision not to name or describe MCAS in standard training materials was a product of the same logic that drove the program from the beginning. Disclosing the system meant explaining why it existed. Explaining why it existed meant acknowledging that the MAX handled differently from previous 737s under certain conditions. Acknowledging that meant undermining the commonality claim. The training omission was not the result of someone deciding that pilot knowledge was unimportant. It was the result of a system in which the commercial argument and the safety argument were never clearly separated, and in which the commercial argument had structural priority. The fifth, after the first crash, the system was defended as procedure before it was admitted as architecture. The response to Lion Air 610 was framed around pilot training and procedure. The existing runaway stabilizer procedure covered the scenario. Pilots needed to know to apply it. The airworthiness directive would address the gap. That framing was technically defensible. The procedure did exist. It was theoretically applicable. What the framing avoided was the architectural question: whether a system with MCAS's authority, fed by a single sensor, undisclosed to pilots, represented a design that should require a different response than a procedural reminder. Ethiopian Airlines 302 answered that question. The congressional investigation that followed produced some of the most direct documentation of the failure mode. Internal Boeing communications showed employees expressing concern about MCAS, about pressure to limit simulator training, about the distance between what pilots knew and what the aircraft could do. One message from 2017 described the aircraft as designed by clowns, supervised by monkeys. It was written by a Boeing employee. It was not shared with the FAA during certification. The investigations found systemic failures at Boeing and at the FAA's oversight structure. The delegation of certification authority to Boeing's own engineers, which had been standard practice for decades, had not been matched with sufficient independent review of systems, whose scope and authority had changed during development. The 737 MAX returned to service in November 2020, after extensive redesign of MCAS, new pilot training requirements that explicitly named and described the system, and revised sensor architecture requiring inputs from both angle of attack sensors before MCAS could activate. The aircraft that returned to service was meaningfully different from the one that had been certified, which meant the one that had been certified had been meaningfully different from what pilots had been told it was. The standard telling of the 737 MAX story reaches for individual villains, executives who prioritize profit, engineers who stayed quiet, regulators who looked away. Those individuals exist in the record, and their choices matter. But the mechanism that produced two crashes was not a conspiracy. It was a system. A commercial constraint became a design requirement. A design requirement shaped what could be disclosed. What could be disclosed shaped what pilots knew. What pilots knew determined what they could do when the system activated. And the system that activated had grown, incrementally, into something that the process evaluating it had not been recalibrated to assess. Each step was taken inside a normal process by people who had reviewed the step before it. No single decision looks, in isolation, like the choice to put 346 people at fatal risk. The chain only becomes visible when you look at all of it. That is always how these chains work. That is why they are so hard to stop. The 737 MAX was certified as a familiar aircraft. It was sold as a familiar aircraft. It was trained as a familiar aircraft. The pilots who flew it in its first year of service had been told, implicitly and explicitly, that what they already knew would be sufficient. It was not sufficient. What failed was not the sensor, though the sensor failed. What failed was the architecture of a system in which a competitive argument had been allowed to function as a safety argument, in which the demonstration that training costs could be kept low had been allowed to stand in for the demonstration that pilots had been given what they needed. The system pushed the nose down. The pilots fought it. They had not been given a full, explicit account of the failure mode they were fighting. They had been told there was little new to know. The failure was real. The cause chain was longer. Next time, another design failure. Another system that taught itself to ignore what it already knew.
Specificity and rank define the order. But fragile architecture can't hold water. It's a cascade of forgotten code. A heavy legacy begins to overload. A